sac117, problem number 1. We've got a merry-go-round, somebody's pushing it, starts out at rest, and it's got an angular acceleration of 0.405 radians per second squared. Let's go ahead and draw a picture of that. We'll get the merry-go-round going around with an angular acceleration of 0.405 radians per second squared. In part A, they want to know how fast the merry-go-round is spinning after 5 seconds. How fast it's spinning is what its angular velocity is, the magnitude of its angular velocity. So part A, we'll start by using one of our constant angular acceleration equations, because they do state that it's a steady angular acceleration of 0.405 radians per second squared. That wording means that it is indeed a constant angular acceleration. So we're justified in using our constant angular acceleration equations. In this one, we want to know what omega is at the end of a certain time period t, and we're given alpha. So we use the equation that involves omega, alpha, and t. That's the one that just reads omega is equal to omega 0, the initial angular velocity, plus alpha, the angular acceleration, times the time t. And we're given that it starts out at rest, so omega sub 0 is 0. Hence, at this point, it's just a plug-in. We'll go ahead and substitute the values, the 0 for omega 0, the given angular acceleration 0.405 radians per second squared, and the time t. And evaluating that, we find that omega is 2.025 radians per second to 3 sig figs. That's just 2.02 radians per second. Okay, in part B, they want to know how many rotations does the merry-go-round complete during the first 5 seconds of its motion. How many rotations? Rotations or revolutions is actually a measure of angle, and it's usually used when the angle is bigger than 360 degrees, but it doesn't have to be. It could be some fraction of one complete rotation. But they're asking for the angle, which is, we generally use the symbol theta to represent the angle. So again, we want to use a constant angular acceleration equation for part B. In this case, they're asking for theta. And let's see, we know t and we know alpha, so we'll pick the angular acceleration equation, the constant angular acceleration equation that's got those quantities in it. Namely, theta is equal to theta 0 plus omega 0 t plus 1/2 alpha t squared. At this point, we can actually pretty much use any of the constant angular acceleration equations, since we also know omega, but it's better, if possible, to go ahead and use the angular acceleration equation, the constant angular acceleration equation involving the given quantities rather than one that you've already calculated. And indeed, it is possible in this case, so we use the one that I've indicated there. Theta 0, we're defining the original angular position to be 0 degrees, and omega 0, it was stated that it started at rest, so that's 0 as well. And in fact, we're solving for theta, so the equation is already solved. We can just go ahead and plug in values. So the first term clearly 0, since theta is 0, omega 0 t is 0 as well, since omega 0 is t, and we just need to evaluate this. Substituting the values with units into the calculator, I get 5.0625 radians for theta. And that's what they were asking for, but they specified that they wanted it in rotations. So we got to convert that angular measure to rotations. Our conversion factor is 1 rotation over 2 pi radians is 1. the way we do all the conversions, just multiply by 1, and 2 pi radians is equal to a revolution. So 1 rotation over 2 pi radians is the form of 1 that we need to get rid of the radian measure there. And evaluating that, I obtain to 3 sig figs 0.800 rotations, and that's our answer for part B. And that does it for SAC 117, problem number 1.